So today we'll discuss about periodic functions and what is the Laplace transform of periodic functions. So we have this periodic functions. So first thing that comes to our mind is that what is a periodic function? A periodic function is one which repeats itself. So suppose this is the given function. Say this axis represents f of t and it represents f, and this point is 0, this point is a, this point is 2a, this point is 3a, and the function from 0 to a is defined like this. And again from a to 2a it is defined like this, and again from 2a to 3a it is defined like this. So you see, after every interval here the function is repeating itself. So that means we are saying this is a periodic function. So we say any function f of t is periodic if f of t plus a is equal to f of t for all values of a. So this is the definition of periodic function. So in particular, what is this function? The name of this function is sawtooth function, and it is defined through this expression. F of t is t whenever it lies between 0 to a, right? So you see, this is a straight line passing through origin y is equal to x, and this is also a straight line, but now this has been displaced by a units, and this is also a straight line y is equal to x, but this has been displaced to 2a units, and so on. So whenever it is between 0 to a, its value is t, otherwise it is f of t plus a. So that means it is periodic function. Another example is that of square wave. So let us see the next example. We have one square wave. It is defined to be f of t, which is plus k, and it is minus k. It is plus k whenever t lies between 0 and a, and it is minus k whenever t lies between a to 2a. So that means the period for this particular function, what is this? This is nothing but 2a. How? So let us first draw this function. This is the t axis, right? Because t is the independent variable here, and this is the f of t axis. So now say this is point 0, this point is a, this point is 2a, this point is 3a, and so on, right? So you see the function is defined from 0 to a. 0 to a its value is k. So say this is k. From 0 to a its value is k. So this is the given function. From a to 2a its value is minus k. So on the negative side, say this is minus k. So from a to minus a its value is this. Again, because this is periodic function, so from 2a to 3a its value would be k, and then from 3a to 4a its value would be 4, and so on. So we can say the function is discontinuous at this point a, and at this point 2a, and at this point 3a, and so on, right? So this is the square function. We are having magnitude as k in the positive direction and in the negative direction as well, and its period is 2a, because after every length 2a this function repeats itself. So that is the periodic function. So now the next task is, why we are studying periodic function here? Because we wanted to see what is the Laplace transform of periodic function. So this is what we are looking for. So to answer this question, we have one result. It says that we have one result. It says that if f of t is given to be piecewise continuous, and it is of exponential order and periodic with period A, then the Laplace transform of the function f of t, that is equal to 1 divided by 1 minus e to the power minus as into integration from 0 to a e to the power minus st f of t dt. So now note here that why all these conditions are required. The condition of piecewise continuity and that of exponential order is required for the function to have the corresponding Laplace transform. So these two conditions are required for the existence of Laplace transform, and the third condition is that of periodicity. The third condition is that of periodicity. It says that the function is periodic with period a. So in that case, the Laplace transform of that function is 1 divided by 1 minus e to the power minus as, where what is this a? This a is the given period of the function, and integration. In the Laplace transform, you take the integration from 0 to infinity. This term is from 0 to infinity, but now we have restricted this term infinity to a. Here what is this a? This is the period of the given function. So 0 to a e to the power minus st ft dt. So this thing is same as the definition for periodic function. So let us see the proof for this result. So this is very simple. So we assume that because it is given in the theorem, or we know because f of t is periodic function, this is a periodic function with period a right. That means you could write f of t plus a is equal to f of t for all t greater than equal to 0, right. So now what we'll do, we'll take the Laplace transform of the given periodic function. So for that, what would be the Laplace transform of f of t? This would be equivalent to its integration from 0 to infinity e to the power minus st ft dt. This is by the definition. So now because the limits here, note that the limits here are from 0 to infinity, so you could break this limit to 0 to a, and then from a to 2a, and then from 2a to 3a, and so on. You keep on doing this until the last limit would be, you say, in between you have this limit na to na plus or n plus 1a, right, n plus 1 into a, and you keep on doing this. So you have all the limits from 0 to infinity. So we are breaking this whole limit as integration 0 to a e to the power minus st ft dt, and then we have integration from a to 2a e to the power minus st ft dt, and plus we have integration from 2a to 3a e to the power minus st ft dt, and so on, right, plus so on. We would have the integration from na to n plus 1a e to the power minus st ft dt, and so on. We would go up to infinity, right. So we have just what we did, we just broke this particular limit from 0 to infinity to all these limits because the given period is a. Okay, so now what we will do, we will substitute in place of t, we will substitute in place of t here, as t would be replaced with v plus a. In this we will write t as t is equal to v plus 2a. In this we will write t as v plus 3a, and so on. Here we would write t as v plus na. So all these intervals we would have different values substituted for t in order to solve this. So what do we have? So the Laplace transform of f of t would now become, so see in this particular integral, what do we have? We would have integration from 0 to a as such, e to the power minus st, then f of t dt, and then in the second integral, I'm sorry, here what we will do, we will substitute t is equal to v plus a into the second expression, not in the first expression. So here this term would come as such. The first term would be integration from 0 to a e to the power minus st ft dt. It would be as such, and then here in place of t we will write v plus a. So here you see what would be dt? dt would be dv, and what would be the limits? Whenever your t is a, what is your v? This implies v is equal to 0, and whenever your t is equal to 2a, your v is what? V is equal to, whenever your t is equal to 2a, then you substitute 2a here in place of t and calculate what is v. So you would have v to be a. So that means you have now converted the limits from 0 to a instead of a to 2a. So this term would now become integration from 0 to a. Here also we would have 0 to a, not from a to a. So it would also be from 0 to a. Okay. So integration from 0 to a, now this quantity would be e to the power minus s. In place of t we would write v plus a, and then in place of f of t we would write f of v plus a, and then in place of dt we would write dv. So this is for the second expression. For the third expression, we will substitute t is equal to v plus 2a here, so that your dt would be dv, and when your t is equal to 2a, what is v? V becomes 0, and whenever your t is equal to 3a, your v becomes a. So here the third integral would be again from 0 to a, e to the power minus s. Instead of t we would now write v plus 2a and f of v plus 2a dv. So this is the third term, and we keep on doing this. For this term, what we'll do, we will substitute t as v plus na, right? V plus na, so that your dt would become dv, and the limits would change. Whenever t is na, your v would become 0, and whenever your t is equal to n plus 1a, your v would become a. So this is what was required, the limits from 0 to a. So the nth term, that would be again from 0 to a, e to the power minus s v plus na into f of v plus na into dv. So let us see what do we have here. Because the given function is periodic, as f of t is periodic, so that means f of t is equal to f of t plus a is equal to f of t plus 2a is equal to so on, that is equal to f of t plus na, right? So if you change the variable f of v, so it would be f of v plus a, which is equal to f of v plus 2a, and so on, f of v plus na. Therefore all these terms, f of t would be f of t, f of v plus a would be f of t, f of v plus 2a would be f of v, f of v plus na would again be f of t. So see what do we have here. So we would have integration from 0 to a, e to the power minus st ft dt, first term. For the second term, you see we would have integration from 0 to a, e to the power minus s into v plus a, and in place of this v, f of v plus a, we would now have f of v, right? F of v dv. And here also we can change the variable. There would be no harm when you change the variable t to v, because that won't affect the value of integral, and this would also be from 0 to a. So 0 to a e to the power minus sv f of v t v, 0 to a e to the power this thing, and the third term, this third term would become integration from 0 to a e to the power minus s v plus 2a into what is this thing? This is f of v. So we have f of v dv plus so on. The nth term would be integration from 0 to a e to the power minus s v plus 2a. V, instead of this v plus na, here it would be the same. Instead of this f of v plus na, it would be f of v dv plus so on. So these are the terms that we have. So now you see what do we have from here when you integrate this, or you could take this term to be so you could open up this brackets and powers. So what do you have? So you would have integration from 0 to a e to the power minus sv fv dv, first term as such, and then in the second term 0 to a integration e to the power minus sv fv dv as such, and this term e to the power minus sa could be taken out of integration because this does not contain v. Similarly, when you open up this term, you would have e to the power minus sv and you would have e to the power minus 2as, right? So again, because this is independent of v, this could be taken out. So you have e to the power minus 2as integration 0 to a e to the power minus sv fv dt dv, and so on. You keep on doing this. For the nth term, what would you have? You would have e to the power minus nas integration 0 to a e to the power minus sv fv dv. So that now you could take this term common, because you see this integral is the same as this one, it is the same as this one, and it is the same as this one. So you could take this integral common. So we would have we would be left with 1 plus e to the power minus sa plus e to the power minus 2as plus so on e to the power minus nas plus so on, because we have infinite series, and here we would have integration from 0 to a e to the power minus sv fv dv. Okay, so what is this? This is an infinite GP. This is an infinite geometric progression, and its common ratio, what is this? When you divide the third term by common ratio, so it would be, when you divide the third term by second term, it would be equivalent to the, when you divide the fourth term by third term, so its common ratio is e to the power minus sa. So its sum, infinite sum would be, what would be this? It would be 1 divided by 1 minus r. So it would be 1 minus e to the power minus sa, right? So this would be the sum of this series. So you could write this whole series here as 1 upon 1 minus e to the power minus sa and this term as such. So it would be integration from 0 to a e to the power minus sv fv dt or dv, right? Not dt, because the integration here is with respect to this variable v. Or in other words, you could write this to be 1 divided by 1 minus e to the power minus sa integration from 0 to a e to the power minus st ft dt. So this is the term that we have with us. So this is what we were intended to prove here. So let us see one example corresponding to this. So the example says you are given this function f of t, which is defined as 1 in the interval a to a by 2, and it is defined to be minus 1 in the interval a by 2 to a. So we are asked find its Laplace transform. So now, because you know this is a periodic function, So, and this is also piecewise continuous and is of exponential order. So therefore we could use the above result, which says that the Laplace transform of some periodic function is given by 1 upon 1 minus e to the power minus as into the integration from 0 to a e to the power minus st ft dt. So this is the result, where what is this a? This a is the period of the given function. So first of all you should note that what is the period of this f of t. This is defined again not from a but from 0. This is defined from 0 to a, right? So it is the period is 0 to the interval length is 0 to a, so its period is also a. So period length is also a, right? So we'll just apply this formula onto this function. So what would be the Laplace transform? It would be 1 upon 1 minus e to the power minus as such, and then integration from 0 to a e to the power minus st. What is ft? ft is defined like this. So what we have to do, we have to break this limit from 0 to a by 2 e to the power minus st ft dt, and then from a by 2 to a e to the power minus st ft dt. So this is the limit that we have. So we could solve this 1 upon 1 minus e to the power minus as. What is the value of function defined between 0 to a by 2? Its value is given to be 1 here, so it would be integration 0 to a by 2 1 into e to the power minus st dt, and then we have integration a by 2 to a minus 1 into e to the power minus st dt. Okay, so we can solve this. It would be 1 upon 1 minus e to the power minus as, and when you perform the integration with respect to t, you would substitute the limits thereafter, and then here you would have minus e to the power minus st divided by minus s, and the limits varies from a by 2 to a. So now you could just substitute the limits of integration. So what do you have finally? It would be 1 divided by 1 minus e to the power minus as, and then it would be minus 1 by s outside because this is constant. So it would be e to the power minus s into a by 2, and then when you substitute 0 here, so it would be e to the power 0 or minus 0, so that would be 1. And then for the second limits, we have 1 by s common, so it would be e to the power minus sa minus e to the power minus sa by 2. So this is the result. So you could simplify this. Now s and s, because it is common, could be taken out. We have 1 upon s 1 minus e to the power minus as, and we are left with 1 minus e to the power minus sa by 2, and here plus e to the power minus sa, and then minus e to the power minus sa by 2. So finally the answer here would be, it would be 1 divided by s into 1 minus e to the power minus as, and then 1 plus e to the power minus as minus 2 e to the power minus as by 2. So this is the final answer, and this is how you calculate the Laplace transform of the given periodic function.